Okay, great. Thank you, Abby, and welcome everybody to the UNC Core Center for Clinical Research Speaker Series. We are very happy and very much appreciate you taking the time to join us today for this presentation. And today, as you can see, we have Jason Franz with us. He's an associate professor in the Joint Department of Biomedical Engineering, joint at UNC Chapel Hill and North Carolina State University. And his presentation today is titled Using Wearable Sensors and Musculoskeletal Simulation to Inform Precision Rehabilitation in Knee Osteoarthritis. So thank you, Jason, and take it away.
Thanks, Todd. I really appreciate the introduction, and thanks to everybody for joining us this morning. I've been looking forward to this for a couple reasons. One is I really like this crowd. I think that this group offers a lot to the University of North Carolina community. It's a big asset, and the other reason is it's given me the chance to really twofold. One is to share some data that I haven't had a chance to talk about, some stuff that's hot off the press. And two, as you'll see, it's giving me the chance over the last week or so to view the other things. It'll be a bit of a bait and switch where certainly going to talk about the things that are in the title, but there's going to be some other things and really taking a step back and viewing the broader research portfolio that we have here in my lab at UNC with regard to osteoarthritis. And so one disclosure off the top here, you would have seen a similar disclosure perhaps as recently as last month with a colleague of mine, business partner, Dr. Brian Petrismon at UNC as well. We do have a company for which I'm the founder and CTO that does develop solutions, wearable sensor solutions for knee OA. Be really clear where the conflicts of interest arise, so you can sort of put that in your back pocket for now. Of course, older adults are one of the largest and most rapidly growing parts of our community worldwide. And as you can see here, the activities that we participate in as we age, they're incredibly diverse. And we all have this shared experience watching our older relatives or people in our communities, our peers, go from being quite strong, quite vigorous, and quite capable to becoming frail, walking slower, having fatigue and exhaustion, and reporting symptoms of knee osteoarthritis, among other things. And you know, oftentimes it doesn't need to be because we have an overt diagnosis, an overt disease or pathology, but it's simply part of the aging process. And I think we can do better by these individuals in our community. And so that's really the driving motivation for the work that we do in my lab. The mission of my lab is to engineer solutions to help people age gracefully. We take a mechanisms-based approach to rehabilitation engineering in everything that we do, and we try to be quite equitable in the research discoveries we make. Of course, you know, the largest portion of this morning's talk is going to be on osteoarthritis and our work in at-risk or diagnosed individuals directly. But we also do a number of other things. And I think I fall prey to this as well. We think about our boutique area of study, perhaps it's osteoarthritis. And oftentimes I and others will forget that the lived experiences of these people are incredibly broad and diverse, and they're doing a lot of things, and they're suffering from a lot of things. Certainly, walking performance is something that becomes more and more challenging as we simply get older. We have a lot of research in this space. Falls are a critical public health challenge that needs to be addressed. And the challenge is it's incredibly complicated, both from a diagnostics and rehabilitation perspective. And then fatigue and exhaustion. You know, your otherwise healthy 80-year-old is walking next to, perhaps on this campus, their 20-year-old fellow or student, and that older adult is consuming oxygen 20, maybe even 30% faster than that average 20-year-old. And the reasons for this are really poorly understood. So that's the broader scope, the broad paintbrush of the research that we do. And sort of alluded to this, what I really want to do with this talk is talk about intersectionality, A lot of the work that we're doing with support from NIH and others is looking at age-related changes and what can be done if we should intervene. But throughout all of this, there's this intersectionality when you layer on something like osteoarthritis that could disproportionately challenge, disproportionately afflict the people that we've been spending our research agenda on for 15 years. And so I'm going to keep coming back to this idea of viewing the whole person and intersectionality between these challenges that are facing these individuals that we are responsible for treating and in the care of. I'm going to start with walking performance. Now, that's very broad. So where do we begin? Well, the single most common biomechanical change, at least in elderly gait, is this reduction in the vigor, the intensity with which we push off the ground with each step. And that's important. That's the way in which we accelerate. We maintain speed. We maintain stride lengths. And instead, what we see is this redistribution of more proximal, less economical muscles. And this this pathway is something that we've thought of and others as contributing to shorter shuffling steps, slower speeds, and worse walking economy. If you look into the literature, there's not a lot of these biomechanical studies, but those that do exist suggest that the opposite happens if you happen to have, in this case, knee osteoarthritis, that there's an avoidance of using those hip and knee muscles, those hip and knee joints to power movement, to redistribute back down to the ankle as a way to avoid knee pain. And so I want to start thinking about this this negative feedback loop where individuals with knee osteoarthritis are now relying more on the muscles that we already know aren't going to be there to catch them if they need that type of support. Now, the calf muscle tendon units, that's what's responsible for generating that push-off intensity. The muscles are your motors, and we've studied those in aging a ton. But the forces transmitted from those motors, they have to go through the series elasticity of the Achilles tendon, and the changes there have been much less well studied. So if we look at just what does age do to the Achilles tendon, one of the most pivotal changes is actually the stiffness of that tissue decreases as we get older. These are the results of a review paper we published just a few years ago that show the vast majority of studies, at least in humans, show a reduction in Achilles tendon stiffness. And I'm going to show you why that matters. But before we do that, just recently going into the literature a little bit, there's some evidence that this could become worse in individuals with osteoarthritis. Knee and ankle osteoarthritis showing decreased soleus, disproportionately decreased soleus size, decreased gastrocnemius strength. You think about more distal to that, ankle osteoarthritis has been associated with a decrease in the width of the Achilles tendon. All of these, directly or indirectly, are going to lead to a decrease in tendon stiffness compared to age-matched controls. Let me show you why that would matter. So imagine you're a young adult and you have a stiff tendon there in green. Now I'm going to replace that green stiff tendon with a floppier rubber band. The force demands of movement don't change. And so now if I'm operating a muscle against a less stiff rubber band, that muscle is going to be driven to shorter lengths. Now we know from basic muscle physiology and the way in which contractile proteins overlap, if you force a muscle to operate at shorter lengths, but you keep the task demands the same, you're going to have to activate that muscle a lot more. And that matters. These higher activations are going to mean that you have to consume more energy to operate that same muscle. Or if you don't activate more, you're going to have a reduction in force generating capacity. It's going to lead to shorter steps, slower speeds, and all of this, ecologically could lead to earlier fatigue. We see this a lot. Aging studies for decades have showed slowed speed with age, increased energy expenditure. But then if you look and then you compare that to between individuals with osteoarthritis and age-matched controls, you see a further exacerbation of these changes. This is not to say that this neuromechanical pathway that I'm about to describe is something that's also exacerbated in people with osteoarthritis, but I would say really interested in looking into this more. Over the last 5 years or so, what we've done is actually to see, theoretically this makes sense, but can we find actual support for this neuromechanical cascade between a reduction in tendon stiffness and all the way up to higher metabolic costs and earlier fatigue? Older tendons are less stiff. We've shown that definitively with ultrasound imaging studies. We've gone over to the UNC Biomedical Research Imaging Center, deployed some really novel high-field MRI data to characterize the tendon. I've even gone out to a place like the Center for Limb Loss and Mobility at the Seattle VA and done cadaver work to demonstrate a lot of this support for this cascade. So that happens. The question is, does that then percolate up and affect muscle and gait function? So the first question is, does that precipitate shorter lengths? And the accumulating data says that yes, these are data from our lab showing that older adults operate their muscle during walking. These are ultrasound data, about 10% shorter lengths than younger adults do. And again, from an excitation perspective, if you have some requisite force demand to walk, but you are being forced to do that with shorter lengths, you should see increased activation and thus increased metabolic cost to walk. And these are data that we just came up with about a month and a half ago. It's the first time that I'm actually able to present on these. So on the left, you see that in these same subjects, older adults are consuming oxygen about 17% faster than their younger adults. But the one on the right is the really novel thing. And this is the first direct link between Achilles tendon stiffness that you see on the x-axis being lesser, driving an increase in metabolic energy cost on the y-axis there. So a direct correlational link between these two outcomes. But let's go a little bit deeper. We've actually used musculoskeletal modeling and simulation. I won't get into too much detail on this work, but you can actually simulate the amount of oxygen being consumed by individual muscles, and we can do that at varied tendon stiffness to show that much of the increase in whole body metabolic energy cost is actually attributed to an increased cost to operate the calf muscles themselves. But let's go even deeper. These shorter calf muscles, again, we've now associated them with decreased stiffness. We've shown that it correlates with increased metabolic energy cost. And that's interesting from a snapshot in time, but what happens over the course of time? And these are data we just finished collecting and analyzing about, again, a month ago, which shows that if you take a person and you, in a controlled experiment, to fatigue, you have them do that task at shorter lengths versus longer lengths. The longer lengths are going to be on the left of these two, the shorter lengths on the right. And shorter lengths yield in this about 60% earlier onset to muscle fatigue. And so this cascade, where it's really interesting, where you can connect the dots, one tissue, tendon to muscle, to its activation, to cost, to actual function, is something we try to do a lot in our research, connecting these dots. So earlier onset of fatigue in these individuals. Let's talk about fatigue. This is not new. I was seeing data as far back as the 60s and 70s, finding associations between higher energy cost and self-reported perceptions of fatigue in individuals with osteoarthritis. And so let me share with you a couple of the paradigms that we use in my lab to study fatigue and some of the discoveries we're making. So the first question I always like to ask is this a meaningful and functionally relevant outcome? And so it turns out that going for a walk for 30 minutes is quite common, whether you happen to be 18 years old or 75 years old. And so what we did is we emulated the 30-minute walk. We had people walk for 30 minutes. And this is just their rate of perceived exertion. We have 18 younger adults in black, 15 older adults in gray. You see over the course of time, the perceived exertion increases. But what I really want you to show is that just by walking for 30 minutes, relatively healthy older adults are already approaching this threshold for vigorous activity, just walking at their usual speed. What do we do with that? Well, we can start to look for biomarkers of fatigue and the electromyographic signals of these muscles. So we'll throw on a lot of EMG measures. And really what we're looking for in the EMG is a fatigue biomarker that's quite common in the literature, which is the decrease in the mean frequency of activation. And then for these different groups, what we can do is we can look at the sensitivity of individual muscles to the time duration of walking. So imagine this is the slope of onset of fatigue over the course of 30 minutes for our younger adults on the top, older adults on the bottom. And one of the things I'm going to point out with this star is the gluteus medius. This is something that doesn't fatigue in younger adults when we go walking, and it does if you happen to be an older adult. And the gluteus medius is really important. It swings your leg out to the side. It controls step width from one step to the next, and that's probably why, and I'll talk about balance and perturbations a little bit later, but when we apply a balance disturbance to these individuals 30 minutes at the end, they're way more vulnerable to these perturbations than they were at the beginning. And it's likely because fatigue matters. It has an ecological impact on our ability to safely navigate our communities. And so the implication there would be, you could imagine deploying EMG, where these are wearable, they're wireless, pretty inexpensive, surface sensors to get a fingerprint of an individual's fatigue. And then that could be used, for example, to guide targeted strengthening interventions, or it could be used in collaboration with some of our robotics colleagues to turn on or cue the assistance from a robotic device. I also really like to dig deep into cause and effect. So that glute med fatigue, it got into my brain. It got in the brain of one of my PhD students, Andy Shelton, who went back and said, okay, so what if we fatigue just this muscle? It seems to be relevant. It seems to be disproportionately afflicted in older adults. Let's see if we, just fatigue this muscle. And so what he did was he took a lot of balance outcomes before and after, a lot of gait outcomes before and after, and did a sidestepping task to fatigue, and fatigued the glute med. You can see that in the median frequency, the isometric force, also getting additional perceptions of fatigue during this task. And we were able to confirm that, yeah, it's really something about glute med fatigue that is contributing to balance impairment at the end of that 30-minute walk. And one of the things that this is steering toward is, many of the individuals, and you can imagine this with knee osteoarthritis as well, we don't prescribe glute med exercises a lot, nor do many of the tasks that we take part in every day use the glute. So for older adults, those muscles are actually weakening at a faster rate than some of our other muscles. And that could be a really important catalyst for targeted interventions. So let me take a pause there and just tell you where we've gone so far. I mentioned that a lot of our work is really focused on biomechanical, neuromechanical changes in aging, how it affects mobility. I'll come back to stability, but now fatigue, and talking about mechanisms that drive that. And then talked a little bit about this notion of intersectionality, where that you layer onto that the diagnosis of knee osteoarthritis or ankle osteoarthritis and the complexities that come along with that. We really have to take a step back and zoom out and view our patients with osteoarthritis through the lens of all of the other challenges that they're facing from one step to the next. But I really want to dig into this, which is, when I think I was able to present to this group a couple years ago, and certainly this line of research, we still consider it quite new, it's maturing, but of all the research that we're participating in, it's the one that we would view as most sort of on the leading edge of at least our contributions. And here, our direct or indirect research is ultimately pointing in the direction of wearable sensors and machine learning for precision rehabilitation. So I want to, talk about that. We and the people on this call are interested in osteoarthritis throughout the lifespan, right? So we have individuals with knee injury early that are then at risk and go on to the diagnosis of osteoarthritis, all the way through to the people that have the diagnosis, are trying to walk without pain, are trying to avoid the knee replacement, and so those age-related joint degenerations. Where did we begin? We really started in a group at risk for knee osteoarthritis. So a lot of the work here in collaboration with colleagues, for example, Dr. Brian Petrosmone, who may have presented on some of this recently. We know that quadriceps dysfunction following ACL reconstruction is accompanied during walking by significant reductions in the knee extensor moment. You can see that on the left, and knee flexion excursion. You can see that on your right. And both of these changes are evidence of quadriceps avoidance during walking, but these clearly an incomplete story, because strengthening interventions, they can restore muscle strength, but those interventions do little to actually mitigate these gait changes. And it's really in vivo ultrasound that could provide a way to look under the hood and discover how these muscles are actually operating to produce knee moments, and the emergent joint contact force is considered so relevant to knee OA. We started here because we have such a strong background in arthritis in ultrasound. And we started with the vastus lateralis because, by its size alone, it's the largest contributor to knee joint moments and knee joint contact forces. And here you see first the length change of the entire muscle tendon unit from proximal to distal bone attachment. We focus on this weight acceptance phase that you see here, during which the knee is flexing and the muscle tendon unit itself is lengthening, while the quads are generating force to resist that. If we image the muscle directly, we actually find something pretty surprising. And that is that as the knee is flexing and the entire muscle tendon unit is lengthening, the quad muscles themselves, at least in uninjured controls here, they're receiving sufficient activation to actually shorten as the joint is being loaded. And what that implies in these individuals is that it's actually tendon lengthening and not muscle lengthening that's more responsible than we previously appreciated to governing quadricep muscle forces during limb loading. And again, that's at least in uninjured control. So what happens after ACL injury and reconstruction? Well, let's retake our ultrasound measurements during walking in individuals 6 to 12 months following surgery. And what we see first here is that the quadricep muscles on the uninjured contralateral limb is largely indistinguishable from those control subjects. But we see fundamentally different behavior on the injured limb. And it's only in the injured limb that we see significant muscle lengthening during limb loading. Something even more surprising, considering that limb is actually going through much less knee flexion than uninjured controls. So what does that actually mean? Why do we care about that? So there's actually two possible explanations. The first is that due to insufficient muscle force, maybe it's weakness, the quadricep muscles themselves may be either succumbing to the task demands of weight acceptance in walking during that early stance phase, or shifting to eccentric action as a compensatory strategy. The second is that these individuals may be operating their muscles in a way to avoid excessive tendon lengthening. And that's really relevant in this group, because all of these individuals received bone patellar bone grafts. But what's also really interesting, and something that we're exploring only now, in fact, this week in the last recent days, is that there's recent evidence from animal studies that eccentric or lengthening muscle action may have fairly significant inflammatory consequences that associate with early signs of cartilage and bone degeneration. So, the takeaway from this here is that quadricep muscle behavior itself may serve as a marker of recovery or a target for intervention to reduce the risk of post-traumatic osteoarthritis, at least in these individuals following ACL reconstruction. And it was really that interaction between muscle function, inflammation, joint mechanics, and ultimately osteoarthritis that inspired our pilot award that we only recently finished up, this pain-mediated effects of quad dysfunction on inflammation and cartilage loading in individuals with OA. We're meeting to talk about the biomarkers tomorrow. We're well underway with our ultrasound imaging analysis. What I really want to do today is talk about some of our biomechanical outcomes that are kind of interesting. And so what we're going to report here are N equals 16 individuals. These are older adults with mild to moderate knee osteoarthritis, and really going to focus in on the knee joint itself. Something you'll be familiar with, knee angle, knee flexion shown here. And as I go through these outcomes, really what I'm going to be reporting are statistically significant associations between the knee biomechanics you're going to see on the right and self-reported knee pain and knee function in these individuals. There's nothing shown on the knee flexion plot over a stride because there was no associations here. And I'm less and less surprised by this. Motion alone doesn't trigger the onset or hasten the progression of knee osteoarthritis. It's much more the dynamics of joint loading that do that. So let's get more dynamic. We're going to take the time derivative. We're going to look at the rate of knee flexion, and you can see here in late stance, more rapid knee flexion is associated with better outcomes, better activities of daily living, better quality of life scores in self-reported surveys. Let's take it another step. Let's become even more dynamic. Let's look at the time derivative of that. Let's look at knee angular acceleration. This is going to be a surrogate for sort of the torque demands about the knee. And similarly there in late stance, we see that more dynamic angular acceleration values also correlate with better total activities of daily living and quality of life surveys. We're going to take it one step further into an area that's much, much less well studied, but at least in the biomechanics community, something that's been getting a lot more attention. We're all familiar with position, velocity, acceleration. Well, if you take the derivative of acceleration, you get something called jerk. This is a marker of smoothness. And here what we see is a few things. Less smooth or more dynamic jerk early associates with better self-reported total. Same with the late. This is really where we start to see lesser self-reported pain, more dynamic trajectories. And so if you look across the board here, what we're seeing is that more dynamic knee biomechanics in individuals with osteoarthritis appear to correlate with better function and lesser pain. And this is really during the phases in which the limb is undergoing rapid changes in force, early stance and late stance. More dynamic knee biomechanics. These are nice because these are readily accessible with wearable sensors, and that's something I'm going to come back to. This notion of more dynamic is something I want to continue as a thread here. But before I do, I've done this a couple of times. This is our advertisement for coming soon now, our high-speed biplane fluoroscopy system. You can see our lab there's equipment in it, right? We're experiencing these deliveries. The installation is happening as we speak. And so very soon we will have something that can do what you might be able to see in this video, which is to reconstruct arthrokinematics of the knee. Maybe now we'll be able to ask questions like, why are those associations there? Why does more dynamic loading early and late stance? How does that correlate with actual, articulation kinematics within the knee joint? And so very soon at a lab near you, we'll be able to start reconstructing some of these things. I said that a bunch on the last slide. I kept saying more dynamic. I said more dynamic a bunch. Let's look at this paper that Elizabeth Bjornson and colleagues just published here at a UNC that we collaborate with. And here, trying to put forth a biomechanical phenotype that's relevant in associating individuals at risk for knee osteoarthritis here in red, those with the diagnosis here in green, blue, and dark blue compared to these controls. And really what you're seeing is less dynamic waveforms. And I think Dr. Petra-Simone did a really good job a couple weeks back sort of laying out what this means. We want to connect dots, right? And so what we've been doing a lot of is trying to connect these limb level loadings to the joint level itself. Why in the world would more dynamic waveforms matter? Well, it's something we all know about cartilage. It's avascular. The way in which cartilage health and homeostasis is maintained is through the exchange of nutrients. This idea of having loading and then lesser loading, squeezing out waste and bringing in nutrients. This is something that does appear to be quite common over the life course of knee osteoarthritis. And the question that we've been asking now for maybe the last year and a half or so is when we observe this at the limb level, what in the world's happening at the level of the cartilage? So my PhD student, and this paper is in review now, said, okay, well, let's use biofeedback to cue changes in limb loading and see how that manifests in the joint loading. And so this is Dr. Mandy Munch now. She graduated last year. Walk on a treadmill and extract peak vertical ground reaction force, just normal. We're going to do this in individuals at risk for osteoarthritis. These individuals following ACL reconstruction, 23 of them. And then what we're going to do is we're going to prescribe some target values on a screen. And a lot of people who have attended some of the talks over the last couple of years may have seen a similar paradigm. We're going to prescribe 5% larger, 5% lesser peak vertical ground reaction force to cue more and less dynamic loading. We're going to look at the time series data, and we're going to pick out those strides that are most representative of those target values. And then you can see here what we're going to do is we're going to simulate the biomechanics of the knee to see if altering limb level loading actually alters in the same way with this phenotype of less or more dynamic, the cartilage contact forces themselves. So I won't get into too much detail here, but we do use a COMAX simulation and OpenSim. This is freely available. You could do it with Mandy's help. We can do it now. It was a big learning curve, but now we have the ability to do full 3D musculoskeletal simulations embedded with 6 degrees of freedom tibiofemoral and patellofemoral kinematics and dynamics, simulating all of the ligament and contact forces, and ultimately arriving at a picture here of stress distributions and pressure distributions in the medial and lateral plateau of the tibia. So let me show you some results of that study. Here we see the vertical ground reaction force. This is no surprise. We guaranteed this in our biofeedback paradigm where we cued more and less dynamic loading. And then what we see is if we do run those simulations, if we look down at the joint contact forces themselves, at least especially on the medial plateau, we see that when we walk with less dynamic waveforms at the limb level, we can be pretty confident that we're seeing those less dynamic profiles at the joint level as well in here in blue. I'm going to look at those in a different way here. Actually, before we do, this is important too. So the impulse, that is the cumulative loading over a stride, that's not different between conditions. So this is not more loading or less loading. It's the shape of the loading profile that matters. And this is, I want to look at that again. If we stretch that limb loading profile across on the bottom, and then look at how this actually plays out in the time course of these pressure distributions, here we have control loading, where you have dark red and then lighter colors and then back to dark red. You have dynamic loading here. If you cue somebody walk with less dynamic limb level loading, you can see this sustained pattern of cartilage loading here. And again, I want to refer you back here to SpongeBob. I'll be that 80-year-old professor using references that nobody remembers eventually, but I think for now, this still fits. And the way in which cartilage health is maintained. Now, once we have those in place, we can start to do some really interesting things. And these are data that a visiting scholar of mine just went out and presented last week at ORSI, which is to say, what happens if I walk this way for the next 2 years? So this is called exposure modeling. And so what we can do is we can take MRIs of these same participants. We can come up with subject-specific geometries of the articulating surfaces. Then we can apply the modeled joint contact forces to that and then have some threshold of stress that is associated with cartilage breakdown. You can do that for normal walking, and you can do that for walking with less, sorry, this is biofeedback cueing more dynamic, this is less dynamic, this is more dynamic. And despite saying more dynamic, the exposure to high stress is actually much less. This is the medial compartment of the knee than it was during normal loading. And you know, if we really want to start connecting dots, which I think we're in the place to do now, you can look all the way back to Brittany Luke-Harkey's paper in 2018 that we published with the exercise science department, Dr. Petra Simones, where they're showing that less dynamic loading is associated with blood biomarkers of more cartilage breakdown. And so now, you know, trying to connect dots between gait function, joint level mechanics, now exposure over accumulation of time, and biomarkers of cartilage breakdown. So these are hot off the press, and we'll be trying to publish those in the next year and continuing down the line of these exposure modeling experiments. Super interesting to me, at least. So I told you a lot about the way in which we have started to better and better understand the specific phenotypes, biomechanical phenotypes of at-risk and previously diagnosed individuals, diving deep into associating gait biomechanics with joint loading and showing that more dynamic is better. It leads to less cumulative exposure. The blood biomarkers are pointing in that direction. There's a ton of evidence that you know, Dr. Petra last time he spoke to this crowd went into. The challenge is that none of these discoveries are going to be able to meet the patient. You know, all of this is relying on expensive, complex, and completely inaccessible laboratory equipment. Clinics are never going to have the capital expenses to purchase this. And so how do we actually translate any of this to our patients? And that's really cue the conflicts of interest. There's a fine line between the research activities that we are conducting in this space and the interests of our company. So I'm going to leave that up here, but I'm going to keep my research hat on because a lot of this is R&D supported through UNC. We've been developing and asking questions about whether or not we can replace the need for laboratory equipment with wearable sensors and machine learning algorithms. And to do this, we've been collaborating a lot with our colleagues at NC State at the Assist Center, developing novel hardware that we've published in wireless body area networks for gait rehabilitation, and then deploying those here. This paper is only going to be available 2 days from now. This is pretty recent, where we wanted to know the number of sensors and their locations that could best predict the outcomes that matter for knee osteoarthritis. In this case, the vertical ground reaction force. So just to walk through what we did, we had a lot of subjects walk normally, then with this biofeedback to drive more and less dynamic loading, wore a lot of sensors, and then did a multi-layer perception neural network to say, can the acceleration signals and different combinations of these predict the measured vertical ground reaction force? And in the published study, we concluded that a waist-only accelerometer could get us pretty close, so about 4% body weight accuracy in predicting the ground reaction force. as with most publications, it takes a while to get that out. And these data are the most recent, which are, if we do even more sophisticated neural networks, we can get that to less than 3, about 2.4, 2.7% body weight using a bit more sophisticated neural networks. And that's with one sensor on the lower back, replacing the need for hundreds of thousands of dollars of laboratory equipment. So what does that look like? Well, many of you are familiar with what it looks like to collect data in a lab. It takes a lot of people and a lot of experience. You have to place markers and you need a fancy treadmill. Those individuals need experience with computer coding and you have to get everything calibrated. But eventually, in our labs, we can measure the vertical ground reaction force and we can then show that value to people in real time and get these individuals to walk and cue them to walk in different ways with biofeedback, with these visits that can last up to 3 hours. Again, the goal of this paper, this research paper, is to replace that now with a single waist-mounted accelerometer that you can put on anywhere. You don't have to be in the lab, it's in the clinic. Immediately get access to those right and left limb compressive forces, use biofeedback, and then go off into the real world and have access to this, monitor over time, and then give the opportunity to you or your treating physician the ability to detect, treat, and monitor these ground reaction forces that seem so relevant to knee osteoarthritis. Where are we going with that? Well, we just recently secured funding from the North Carolina Biotechnology Center to start steering the biofeedback with the real-time machine learning models and the wearable sensors to see if those are effective at allowing us to modulate gait biomechanics, and then coupling that with a lot of the modeling and simulation I've already shown you to demonstrate that when we do so, we can also steer local joint mechanics into what we would deem to be healthier patterns of loading. So results not found. We will be getting started on that very soon. It's a 2-year project that just got underway. If I could, I'm going to return to this as I close out the talk. This is a slide you've already seen, but I held something back. There was actually an additional correlation that I hadn't shown you before, and I'm going to reveal it now. There were some things associated with worse scores, and it wasn't anything about the magnitude of these, but instead, it was how variable this outcome was from one step to the next. How the rate of knee flexion, early in stance and late in stance, if you had more of that, you actually self-reported worse knee function symptoms, worse activity of daily living scores. Step-to-step variability. This is not a conversation about whether it's good or bad, but I will be steering you in a direction, at least by these data, that higher levels of variability are indicative of worse knee joint control. And control is really important. Control, when I think of control, I start to get into our research and balance and falls. And so that's sort of where I want to go with this. Now, this is an interesting one, and this isn't unfamiliar to this crowd, but it is something that has started to get more and more traction, this notion of knee osteoarthritis and falls. You can see colleagues that are on the line right now understanding, recognizing this, but it's really been recently where the number of publications have started to soar. And one of the things that's most pointed to here is a decrease in the integrity of sensation, proprioception, somatosensation. And so I really want you to keep that in mind about perception and sensing problems in individuals with osteoarthritis. As I share with you a protocol that I think, I'm really excited about finding new ways to deploy this. And I'm thinking this might be a good opportunity. It is going to use balance perturbations. Balance perturbations, I think, are very, very important for a number of reasons. The foremost, instability that you would measure during usual walking, it fails to predict how vulnerable one might be if something unexpected happens in the community. And vulnerability to balance challenges is incredibly complex. There are a lot of different perturbation types in our lab. I'm not going to show these videos for the sake of time, but if you get bumped at a bus stop, if you slip on ice, if you have innate sensory motor noise and pathologies, the way in which that causes you to be unstable is fundamentally different. The structure of that instability differs based on the context of the balance challenge that you're faced with. Here's the protocol. We've been really, really interested in, and there's some wearable sensors that are going to come up here, the threshold for detection of instability. Only if I detect instability can I do something about it. If instability goes unnoticed, I would have less of a chance to react, to have feed-forward volitional control of my response to instability. And so what we're going to do is we're going to have somebody walk on the treadmill, and every so often, over the course of 15 or 20 minutes, we are going to deploy a rapid deceleration of one belt. Feels like you're slipping on ice if you have a large amplitude. But we're also going to deliver these sub-threshold disturbances. We're going to ask you then, did you feel that? And we're going to be able to, these are in young adults, these will be submitted for publication soon. There's a threshold above which you would say, yeah, I noticed something. Above threshold means I can do something volitionally to arrest the fall. And it turns out the magnitude of that is about 0.06 meters per second, the change in velocity that I can consciously perceive if I'm a young adult. I'm going to put that value up here in the right-hand corner. And then I'm going to throw in some muscle activations. Local muscle detection with EMG, these reflex activations, it turns out that those local muscles distal in the limb, they're actually more sensitive than you are to detecting the instability. That makes sense? These are spinal reflex pathways, and theirs are actually really good at a magnitude of 0.035 to 0.05 meters per second. So those are detecting things quite well. We really wanted to deploy wearable sensors and see if inertial measurement units put on the sacrum, the waist, maybe the right wrist or the right lower leg. Turns out those were pretty poor at detecting instability, definitely worse than you at saying, I felt it. If you ask the sensor, did you feel it? Pretty unreliable. That's okay, because if you use sensor fusion, you can get something like ankle angle from the IMUs. Turns out that's extremely sensitive to at least this type of perturbation. So as I close out, what are we doing from this now? Well, if you repeat this experiment in older adults, which we're doing, we have to do more of, at least so far, this notion of did you feel that? That conscious perception threshold is twice as large for older adults. I don't know. We didn't screen for individuals with osteoarthritis or not, or it's likely that some of these people do have this osteoarthritis, but I think I'm really interested in understanding the interaction between osteoarthritis, sensory perception integrity, and the extent to which how their performance on a task like this is screening, diagnostics, and risk factor assessment. And so that's a direction that I would be really interested in going. So just to close here, again, my goal was to talk about intersectionality between what we know about how aging affects walking performance, fatigue and fatigability, susceptibility for falls, some of the work that we're doing there at the end, but really view it through this lens of the way in which older adults with knee osteoarthritis could be disproportionately afflicted or vulnerable to our mechanistic discoveries and really trying to drive future collaborative efforts and lay the groundwork for future conversations to talk about new studies that we could do, and all trying to, again, engineer solutions to help people age gracefully, prevent falls, be pain-free, because there's a real societal need here. I really want to thank the members of our team, of course, our wonderful collaborators. Purple is the joint department between UNC and NC State, but these are affiliates of either of those institutions, as well as collaborators we have on these projects around the globe. and with and our funding, of course, appreciate our funding for all of these projects. And with that, be happy to take any questions. I've got my contact information if we run out of time. I appreciate you listening.
All right, thank you so much, Jason. We have some time for questions, and I welcome you to unmute and ask your questions, or I'll also be monitoring chat if you'd like to place it there. So feel free to ask your questions, and I can relate to feeling like the 80-year-old professor. So please let me know if there's any way I can help Pig in your. So other questions?
I see one quick from Jason Kim in the chat. Oxygen consumption, sure. So here, we're actually putting oxygen sensors on. You're wearing a mask, and we're measuring the rates of oxygen consumption, rates of carbon dioxide production at the level of the whole body. But our models can actually simulate heat at the level of the muscle, the cost of work, the cost of heat generation. And so the simulated oxygen consumption can be muscle specific if you model it the right way.
Hey, Jason, that was a fantastic
And I see Richard.
talk.
Richard.
Hey, Richard.
Hi. Like over 30 years ago, there was an orthopedic surgeon, Eric Radin, who talked about how changes in proprioception affecting gait are involved in OA, and he used this term microclutzing. And it seems like that's somewhat what you're doing now with the very sophisticated gait analysis and the sensors. So I thought that was really interesting how that's come right back.
I love that idea because really, when I talk about just our balance work, I get into it way deeper. But this notion that there's all this stuff brewing under the surface that can precipitate that first fall. And it's that micro clutzing that you're talking about that we miss a lot of, the diagnostics fail to pick up on. And it's really when you start to disrupt things that you see. But yeah, it's interesting coming full circle to hear that.
Yeah. And I had a question early on when you were talking about tendon stiffness and talked about how it's reduced with age, which was surprising to me because most tissues that have a lot of collagen get stiffer with age because of advanced glycation end products and everything causing cross-linking. So is there something different about, say, the Achilles where it gets less stiff with age compared to other tissues, or how do you explain that?
Yeah, so three things come to mind. The first is that the muscles attached to tendons increase in stiffness because there's, like, as you said, there's a proliferation of non-contractile tissue that embeds itself in the muscle, and its stiffness increases. Collagen cross-linking is also a thing in the Achilles, but it's not within regions of tendons. It's actually across regions of tendons that are associated with different muscles. We have a whole line of research on a healthy shearing that occurs in young adults that sort of develop Velcro, and you don't get that. The literature is quite clear on if you apply a force, tendon will stretch more for that force if that tendon happens to become from an older individual. It could be disuse or less common force transmission, and so tendon is a mechanically adaptive tissue. If it experiences lesser loading chronically, it will experience those types of changes. And so maybe I'll just leave it at that.
Thanks.
I see a lot of hands. I get to talk to Brian all the time.
Yeah, Brian?
If you want to take somebody else's, go ahead. I think that's what you're about to say.
I was about to do that. So Lee or Carla?
Hi, Jason. This is Carla Hill. Building off of what he was just saying, I thought that was interesting as well with the reduced stiffness in the Achilles. We often see reduced dorsiflexion in our older adults and consider that a potential risk factors for falling that we try to address in physical therapy through stretching. So considering where that's at, would you still make a recommendation that we do static stretching of that area, or are we actually potentially making the tendon even more pliable, and we need to be more specific in trying to reduce muscle stiffness as opposed to just a generalized dorsiflexion stretch.
Yeah, no, it's a really good question. So stretching is going to be really good. It is going to counteract the effects of aging on the muscle stiffness, which I think is going to be really important. Decreased dorsiflexion range of motion is due to that. The other thing is, I actually don't think that static stretching is going to reach the force level. The tendon, it can experience force levels of 6,000 newtons and be totally fine. Static stretching is probably not going to reach the threshold needed to make matters worse. So I actually think it would be just fine. And as you said, there's reason to believe that increasing that range of motion would be a valuable thing to gain in our patient.
Lee?
Great talk, Jason. Thank you. I wanted to comment. One will probably be reaching out to you from the Action Alliance, particularly with this balance, OA and balance, because I don't know if your thinking's going, when we think of the public health agenda, one of the 4 areas is injury prevention. And we've thought so much about preventing ACL injury, but preventing falls in people who already have OA is an important injury prevention public health focus. And I think what you're doing could lead to some real interesting public health interventions. And I wonder if you
I'm so interested in that. Yeah, I think it was over just the last week or so. I know we're short on time, but not often do we get the opportunity to take a step back and say, okay, so all this research you do, how is it relevant to that? I found myself in the weeds in papers, and all it did was get me really excited. So yeah, I would love to talk more.
There is one more question in the chat, and maybe I'll let you read that rather than me try to interpret all of that.
PGRF related to improvements in functional assessments like 6-minute walk or sit to stand. Jason, if you could email me, let's chat about that, because I want to say something, but I don't want to be incorrect, and I want to confirm something offline. So I appreciate your question for sure. This is important, right? You want to know that the things that you measure from sophisticated biomechanics are functionally meaningful, and certainly walking endurance like you might get from the 6-minute walk or sit to stand, which is correlated with so many other functional things, are where you would want to look.
Okay, well, I think we're at time, and I really appreciate you spending time with us, Jason, and sharing all this very interesting information. Thank you, everyone else, for joining us. Please do keep in mind, we will be launching a poll, just a few questions, so please take a minute to answer that. And again, thank you very much, Jason, for a great talk. Have a great